Marcus Chen stood at his cabin door, watching his neighbor Jim frantically cover 3 cords of soaked firewood with tarps that should have been secured 2 days ago. Inside the earth-sheltered structure behind Marcus, his son Tommy was stacking bone-dry split oak in the stone alcove where it had remained protected through 72 hours of freezing rain that had devastated every other woodpile in their rural Minnesota township. Before we dive into how one engineer's ridiculed design became the most talked-about structure in the county, let us know where you're watching from. And if stories about unconventional thinking inspire you, hit that subscribe button because tomorrow's story proves that sometimes the craziest ideas are just ahead of their time. The freezing rain began on November 7, 2019, 3 hours before dawn. Marcus Chen woke to the sound of ice pellets hammering against the small windows of his semi-underground cabin. A sound that would have alarmed most homeowners, but only made him pull the quilt tighter around his shoulders. The temperature inside remained a steady 66 degrees despite the assault outside, the earth-sheltered walls doing exactly what he had calculated they would do 18 months earlier when neighbors had laughed at his architectural drawings. By mid-morning, the storm had intensified into something the National Weather Service was calling a once-in-20-years event. Freezing rain accumulated at a rate of 1/4 inch per hour, coating everything exposed to the sky in a thick shell of ice. Marcus stood at his door with his 10-year-old son Tommy and their German Shepherd Bear, watching the transformation of their 5-acre property into a crystalline landscape that would have been beautiful if it were not so destructive. Across the gravel road that separated their land from the Hendersons' place, Marcus could see Jim Henderson outside in his Carhartt coveralls, desperately trying to stretch blue tarps over his firewood pile. The wood had been stacked in traditional crisscross rows in an open area beside his garage, exposed to the elements except for a small roof overhang that proved utterly inadequate against horizontal freezing rain. Jim's firewood represented his family's primary heat source for the winter, nearly 4 cords of split maple and oak that he had cut, split, and stacked over the previous summer. Now it was absorbing moisture at a catastrophic rate. Tommy pressed his face against the glass. "Dad, why didn't Mr. Henderson cover his wood before the storm?" The boy's breath fogged the window as he spoke. Marcus watched Jim struggling with the tarp, the fabric stiff and uncooperative in the freezing precipitation. He probably thought he had time. Weather forecasts said the rain would stay liquid. They were wrong. Marcus did not say what he was thinking, which was that Jim's firewood was already compromised. Freezing rain had a way of penetrating wood piles through capillary action and freezing inside the cellular structure of the wood itself. Even if Jim managed to cover it now, the damage was done. "Our firewood's okay though, right?" Tommy asked. Marcus nodded toward the northern exposure of their cabin, where the firewood alcoves were built into the structure itself. 3 separate storage areas, each capable of holding 1 full cord of wood, were recessed into the exterior walls and protected by the massive overhang of the living roof. The design placed the wood under 5 feet of horizontal protection, keeping it dry even during severe weather events with wind-driven precipitation. The alcoves also benefited from radiant heat that escaped through the cabin walls, creating a passive drying effect that actually improved wood quality over time. "Our wood's fine," Marcus said. "It's been fine all month." Tommy smiled and headed back to his room. Marcus remained at the door, watching Jim Henderson fight a losing battle against November in Minnesota, and remembered the day 18 months ago when Jim had called his cabin design the dumbest thing he had ever seen. The conversation that defined Marcus Chen's relationship with his neighbors happened on May 12, 2018, at a Saturday morning gathering that passed for a community meeting in their rural township. 7 families lived along the 2-mile stretch of County Road 43, and they met quarterly at the Hendersons' garage to discuss shared concerns like road maintenance, snow plowing contracts, and occasionally building projects that might affect property values. Marcus brought his architectural drawings rolled up in a cardboard tube, along with a 3-ring binder containing engineering calculations, soil reports, and climate data he had compiled over 6 months of research. His wife Sarah stayed home, still recovering from her second round of chemotherapy, and Marcus was grateful she did not have to witness what was about to unfold. Tommy was at his grandmother's house, which was also fortunate because 10-year-olds did not need to hear adults ridicule their father's ideas. Jim Henderson opened the meeting by asking if anyone had new business to discuss. Marcus raised his hand and unrolled his drawings on the Hendersons' workbench, weighing down the corners with a hammer and a can of wood stain. The drawing showed a structure that looked nothing like the conventional homes that lined County Road 43. Where those homes sat on raised foundations with peaked roofs and vinyl siding, Marcus's design showed a building that nestled into the earth itself, with walls partially buried and a roof covered in soil and native grasses. "It's called earth-sheltered architecture," Marcus explained to the 7 neighbors who gathered around the workbench. "The principle is thermal mass. Earth maintains a relatively constant temperature of around 55 degrees year-round at depths below 6 feet. By building into the earth and covering the structure with soil, we create a building envelope that requires minimal energy for heating and cooling." Jim Henderson studied the drawing for perhaps 15 seconds before he started laughing. It was not a polite chuckle, but a full belly laugh that made his considerable gut shake beneath his flannel shirt. "You're building a bunker? What are you, some kind of prepper waiting for the apocalypse?" The other neighbors joined in the laughter, and Marcus felt his face flush. He had anticipated skepticism, but not outright mockery. "It's not a bunker," he said quietly. "It's a passive house design that's been used successfully for thousands of years in various climates. Iceland, Scandinavia, even the Great Plains of the United States had sod houses that kept families comfortable in extreme weather." "Sod houses," repeated Karen Mills from 3 properties down. "Those were poverty shelters, Marcus. People lived in those because they had nothing else. You're a structural engineer with a good job. Why would you choose to live like a settler from 1870? Marcus pulled out his binder and opened it to a page showing his calculations. "Because Sarah's medical bills have put us $200,000 in debt, and because conventional construction would cost us $300,000 minimum for a house that would then require another $3,000 per year in heating and cooling costs. This design costs $120,000 to build and will require less than $500 per year in energy costs." The laughter stopped, but the skepticism remained written on every face. Sarah's illness was known throughout the community, and using it as justification for an unconventional building made his neighbors uncomfortable. They looked away from the drawings, suddenly interested in their boots or the oil stains on Henderson's garage floor. "Look," Jim said, his voice softer but still patronizing. "I get that you're in a tough spot, Marcus. We all do. But building some kind of underground bunker isn't going to help your property value, and it sure as hell isn't going to help ours. That thing's going to look like a grass-covered mound in the middle of your lot. It's going to look like a tomb." Marcus rolled up his drawings without responding and walked back to his truck, knowing that asking for approval had been a mistake, but that township regulations required notification of any non-standard construction within the community planning zone. Marcus Chen had not always been interested in alternative architecture. For 15 years, he had worked as a structural engineer for a firm in Minneapolis that specialized in commercial buildings, hospitals, and parking structures. He understood steel and concrete, load calculations and wind shear, building codes, and safety factors. His world was one of conventional design executed with precision, and he had never questioned the fundamental assumptions underlying how buildings were constructed in the modern American landscape. That changed in March of 2017 when Sarah was diagnosed with stage 3 breast cancer. The diagnosis came with a treatment plan that included surgery, chemotherapy, radiation, and a pharmaceutical regimen that would extend for years. Their health insurance covered most of the costs, but most was not all. Co-pays, deductibles, out-of-network specialists, experimental treatments that insurance deemed unnecessary, all of it accumulated into a mountain of medical debt that grew faster than Marcus could pay it down. By the end of 2017, they had burned through their savings, taken out a second mortgage on their small house in the suburbs, and were facing the reality that Sarah's illness would likely require ongoing treatment for the remainder of her life. The financial stress compounded the emotional weight of watching his wife fight for survival. And Marcus found himself lying awake at night doing calculations in his head, trying to find a mathematical solution to an impossible problem. The idea came to him during one of those sleepless nights in January of 2018. He was thinking about their retirement plans, which had always included building a small home on the 5 acres of wooded land they owned 90 miles north of Minneapolis. They had purchased the land 8 years earlier as an investment and a future home site, imagining a conventional cabin where they could escape the city and eventually retire. But conventional construction was expensive, and their destroyed finances made that dream impossible. Unless he changed the fundamental assumptions about what a house needed to be. Marcus started researching earth-sheltered architecture the next morning. He discovered that humans had been building into the earth for thousands of years, not just as poverty shelters, but as sophisticated dwellings that provided superior protection from climate extremes. Icelandic turf houses had kept families comfortable through Arctic winters. Chinese Yaodong cave dwellings housed millions of people in the Loess Plateau. Native American pit houses in the Southwest maintained cool interiors during scorching summers. The physics were elegant. Earth had high thermal mass, meaning it absorbed and released heat slowly. At depths below 6 feet, soil temperature remained nearly constant regardless of air temperature fluctuations above ground. A structure built into the earth, or covered with earth, could leverage this thermal stability, requiring minimal energy input to maintain comfortable interior temperatures. In winter, the earth prevented heat loss. In summer, it prevented heat gain. The building envelope became a moderator rather than a barrier, working with natural systems rather than against them. Modern earth-sheltered architecture had evolved significantly beyond historical examples. Waterproofing technologies, insulation materials, and structural engineering techniques allowed for sophisticated designs that eliminated the problems of dampness, darkness, and structural failure that had plagued older earth contact structures. Marcus found examples of beautiful contemporary earth-sheltered homes in Switzerland, Germany, and even in several locations across the United States. The economic argument was compelling. Excavation costs were lower than foundation construction for a comparable above-ground structure. Reduced exterior wall surface meant less material cost. The living roof, while initially expensive, eliminated the need for conventional roofing materials that required replacement every 15 to 25 years. Most significantly, energy costs dropped by 70 to 90% compared to conventional construction, saving thousands of dollars annually. Marcus spent 3 months designing their cabin, working late into the night after Tommy went to bed, refining calculations and solving engineering challenges. Sarah watched his obsession grow with a mixture of concern and hope. She understood that the project had become more than just a cost-saving measure. It had become Marcus's way of fighting back against the helplessness he felt watching her illness. By May of 2018, Marcus had a complete design, engineered to meet building codes and optimize for the climate conditions of northern Minnesota. He knew the design was sound. What he had not anticipated was the social cost of building something his neighbors could not understand. After the disastrous community meeting, Marcus doubled down on his research. If his neighbors thought earth-sheltered architecture was foolish, he would prove them wrong through sheer accumulation of evidence. He transformed their dining room into a research center, covering the table with books, printouts of academic papers, and photographs of earth-sheltered structures from around the world. Sarah teased him about his obsession, but she understood that the project had given him something concrete to focus on, while everything else in their lives felt uncertain. Marcus started with the historical precedents, wanting to understand not just the successes, but also the failures of building underground. He learned that the earliest known earth-sheltered dwellings dated back more than 5,000 years to the Neolithic period. The Skara Brae settlement in Scotland, built around 3000 BCE, consisted of stone houses covered with earth and turf, connected by covered passageways. The structures had survived 5 millennia because they were built using principles that remained valid. Protection from wind, thermal mass for temperature regulation, and careful attention to water management. Iceland's turf houses represented perhaps the most successful long-term application of earth-sheltered design. From the 9th century through the early 20th century, Icelanders built homes with stone or timber frameworks covered with layers of turf. The design evolved over centuries, incorporating features like enclosed entryways to prevent heat loss, small windows positioned to maximize limited sunlight, and drainage systems to channel water away from living spaces. These houses kept families comfortable through Arctic winters, where exterior temperatures dropped to -20 degrees Fahrenheit, using minimal fuel for heating. The North American prairie presented similar challenges and inspired similar solutions. When settlers moved on to the Great Plains in the mid-1800s, timber was scarce and winters were brutal. Families built sod houses by stacking blocks of prairie sod 2 to 3 feet thick, creating walls with extraordinary insulating properties. A well-built sod house maintained interior temperatures around 50 degrees, even when exterior temperatures dropped below zero, requiring only a small stove for additional heating. The structures were dark and sometimes leaked during heavy rains, but they solved the fundamental problem of survival in an extreme environment with limited resources. Marcus also studied the failures. He learned that early earth contact structures often suffered from water infiltration because builders did not understand hydrostatic pressure or capillary action. Stone and sod walls without proper moisture barriers would gradually saturate, creating damp, unhealthy living conditions that bred mold and respiratory illness. Inadequate drainage around structures caused foundations to shift and walls to collapse. Insufficient ventilation led to poor air quality and carbon monoxide poisoning from heating fires. Modern earth-sheltered architecture solved these problems through engineering and material science. Waterproofing membranes created absolute barriers against moisture intrusion. Synthetic insulation materials provided thermal resistance even when damp. Mechanical ventilation systems ensured fresh air circulation. Structural concrete and steel framing eliminated the risk of collapse. The principles remained the same as historical examples, but the execution had evolved to eliminate the drawbacks. Marcus found contemporary examples that proved earth-sheltered design could be both practical and beautiful. The Vals thermal baths in Switzerland, designed by architect Peter Zumthor, featured stone and concrete structures partially embedded in a mountainside, creating spaces that felt both ancient and modern. The Green Magic Homes Company manufactured prefabricated earth-sheltered structures that could be assembled in weeks and covered with soil to blend seamlessly into natural landscapes. Malcolm Wells, an American architect who designed dozens of earth-sheltered buildings in the 1970s and 80s, had published detailed technical manuals showing how to design and build these structures to modern code standards. The passive house movement provided additional validation. Passive houses used super insulation, airtight construction, and heat recovery ventilation to reduce energy consumption by 80 to 90% compared to conventional buildings. Earth-sheltered structures achieved similar results through different means, using thermal mass and earth contact rather than extreme insulation. Both approaches proved that dramatic energy reduction was possible without sacrificing comfort. Marcus compiled climate data for their specific location in northern Minnesota. Average January temperatures range from 5 to 20 degrees Fahrenheit. Average July temperatures range from 70 to 85 degrees. Annual precipitation totaled 30 inches, with significant snowfall from November through March. The frost line extended down to 42 inches, meaning any foundation had to go deeper to prevent frost heaving. Soil composition was primarily sandy loam with good drainage characteristics, ideal for earth-sheltered construction. He calculated heat loss coefficients for various wall configurations, comparing conventional stick frame construction with his earth-sheltered design. A conventional wall with 6 inches of fiberglass insulation had an R value around 19. His design, with 8 inches of rigid foam insulation on the exterior of concrete walls, plus 4 feet of earth cover, achieved an effective R value exceeding 50. The difference would translate to heating costs of perhaps $300 per year versus $2,000 or more for a conventional structure of comparable size. By June of 2018, Marcus had enough data to confidently proceed. He did not need his neighbors' approval, only their notification that he had complied with township planning requirements. The Henderson meeting had satisfied that legal obligation. What happened next would prove whether his calculations were correct or whether Jim Henderson's mockery was justified. The county building department occupied a dingy office in the basement of the courthouse in Pine River, Minnesota. Marcus arrived on June 4, 2018, with his architectural drawings, structural calculations, and a growing sense that bureaucratic resistance would prove more difficult than engineering challenges. The building inspector assigned to his case was a man named Dale Sorensen, 63 years old, 2 years from retirement, and deeply suspicious of anything that deviated from the residential building patterns he had approved for 4 decades. Dale spread Marcus's drawings across his desk and studied them in silence for nearly 5 minutes. Marcus watched the inspector's face cycle through confusion, skepticism, and what appeared to be irritation that someone had brought him something requiring actual thought rather than rubber stamp approval. The office smelled of old coffee and photocopier toner, and Marcus could hear the muffled sounds of court proceedings from the floor above. "This is a house?" Dale finally asked, tapping the elevation drawing with a thick finger. "It's a single-family dwelling designed using earth-sheltered architecture principles," Marcus said. "All structural elements meet or exceed code requirements. I've included calculations for snow load, wind load, and seismic factors, though seismic isn't really a concern in Minnesota. The concrete walls are engineered to withstand lateral earth pressure with a safety factor of 3. Waterproofing exceeds commercial basement standards." Dale flipped through the pages without reading them carefully. "I've been inspecting buildings for 41 years, and I've never seen anything like this. That tells me something." "It tells you that most people build conventional structures," Marcus replied, keeping his voice level. "It doesn't tell you that alternative designs are unsafe or non-compliant with code." The inspector pulled out his copy of the International Residential Code and began searching for relevant sections. Marcus had anticipated this and had already flagged the applicable pages in his own copy. Earth-sheltered structures existed in a gray area within building codes. They were not explicitly forbidden, but neither were they explicitly addressed. The code specified requirements for foundations, walls, roofs, and structural systems without mandating specific construction methods. As long as a design met performance standards for structural integrity, fire safety, egress, and habitability, it could theoretically be approved. The next 2 hours devolved into a technical argument about interpretation. Dale insisted that earth-covered roofs violated code provisions about roof drainage. Marcus demonstrated that his design included multiple drainage layers and waterproofing systems superior to conventional roofing. Dale questioned whether the small windows provided adequate egress in case of fire. Marcus showed calculations proving that his windows exceeded minimum egress area requirements and included detailed specifications for emergency escape hardware. The most contentious issue involved the living roof itself. Dale argued that placing soil on a roof created an unacceptable live load that exceeded standard structural design. Marcus countered with calculations showing that his roof structure was engineered to support a saturated soil load of 150 pounds per square foot, far exceeding the minimum snow load requirement of 60 pounds per square foot for their climate zone. The living roof would never approach the weight capacity of worst-case snow accumulation, and unlike snow, soil load was permanent and predictable, making it actually easier to engineer for. "I don't care what your calculations say," Dale finally stated, his frustration obvious. "I'm not approving something that looks like this without getting it reviewed by a professional engineer licensed in Minnesota." Marcus pulled out his business card and placed it on the desk. "I am a professional engineer licensed in Minnesota. License number 43,218. Structural specialty. 15 years of experience designing commercial and institutional buildings. I've engineered structures significantly more complex than this cabin." Dale looked at the business card, then back at Marcus, his face reddening slightly. The power dynamic had shifted. An inspector could challenge a homeowner's competence, but challenging a licensed engineer's calculations was different territory. If Dale rejected the design and Marcus appealed to the county board, Marcus's professional credentials would carry significant weight. "I still want a third-party review," Dale said, but his voice had lost its certainty. Marcus had expected this and had already contacted a structural engineering firm in Duluth willing to conduct a peer review. "I've arranged for Northland Engineering Associates to review my complete structural design. They'll provide a sealed letter confirming code compliance. Will that satisfy your requirements?" Dale nodded reluctantly. "I also want to see your waterproofing specification in more detail, and I want confirmation from the health department that your ventilation system meets indoor air quality standards. And you'll need to schedule inspections at every phase of construction: foundation, framing, waterproofing, electrical, plumbing, mechanical, and final. No covering anything up without me seeing it first." "Agreed," Marcus said. He understood that Dale was protecting his own liability. If something went wrong with an unconventional structure, the building inspector who approved it would face questions. By requiring extensive documentation and frequent inspections, Dale was building a paper trail that demonstrated due diligence. The peer review from Northland Engineering took 3 weeks and cost Marcus $2,000 he could barely afford. The engineers found no faults with his structural design and provided a detailed letter confirming that all elements met or exceeded International Residential Code requirements. The health department approved his ventilation specifications after requesting minor modifications to ensure adequate fresh air circulation in a structure with limited window area. On July 16, 2018, Marcus received his building permit. The approval came with 14 specific conditions, more than double the typical number for conventional construction, but it was approval nonetheless. Dale Sorensen had signed the permit himself, though Marcus suspected the inspector hoped the project would encounter problems that would validate his initial skepticism. Marcus drove home with the permit on the passenger seat of his truck and found Sarah sitting on their suburban porch, wearing a scarf to cover the hair loss from chemotherapy. He showed her the stamped and signed permit, and she smiled for the first time in weeks. "When do we start?" she asked. "Next week," Marcus said, "as soon as I can get excavation contractors scheduled." The excavation began on July 23, 2018, under a cloudless sky that promised temperatures in the mid-80s by afternoon. Marcus had hired Johnson Excavating, a local company that normally dug basements for conventional homes, but was willing to tackle his unusual project for a fair price. The owner, Mike Johnson, arrived at 7 in the morning with a John Deere excavator and a skeptical expression that Marcus had learned to recognize as the default reaction to his design. The 5-acre property was heavily wooded with mature oak, birch, and pine. Marcus had selected a building site on the southern portion of the lot where a natural clearing reduced the number of trees requiring removal. The location provided good solar exposure for the south-facing windows while maintaining forest cover on the north, east, and west sides for wind protection. The ground sloped gently from north to south, perfect for earth-sheltered construction because it allowed for a walkout entrance on the southern exposure, while the northern portion could be bermed with excavated soil. Tommy arrived with his grandmother at 8 o'clock, excited to watch the excavation process. The boy had inherited his father's interest in how things worked, and he spent the morning asking questions about the excavator's hydraulic systems and the properties of different soil layers. Marcus answered patiently, between directing Mike Johnson on the precise dimensions and depths required for the structure. Earth-sheltered construction began not with a foundation hole, but with careful removal of topsoil. Marcus had specified that the top 18 inches of organic soil should be stripped and stockpiled separately from the subsoil. The topsoil would be used later for the living roof, providing the microbial community and nutrient content necessary for establishing native grasses. Mixing topsoil with subsoil would compromise its quality, so Mike carefully scraped it away and piled it on the eastern side of the clearing. Beneath the topsoil, they encountered the sandy loam subsoil that Marcus's soil reports had documented. This layer extended down approximately 6 feet before transitioning to denser clay. The sandy loam was ideal for construction because it drained well and was easy to excavate while still providing adequate bearing capacity for the concrete walls. Marcus had designed the structure to sit on this sandy loam layer rather than going deeper to clay. Another cost saving compared to conventional construction that typically required excavation to undisturbed soil or bedrock. The excavation dimensions were unusual compared to a typical basement hole. Marcus's design called for a rectangular pit measuring 42 feet by 30 feet, but only the northern half would be excavated to the full depth of 8 feet. The southern half stepped down gradually, creating a bermed entrance area where the structure would emerge from the earth at ground level. This configuration allowed for a walkout entrance with standard doors and windows on the south face, while the back and sides of the structure would be completely earth-sheltered. By noon, Mike Johnson had excavated roughly half the required volume. Marcus inspected the work carefully, checking depths with a laser level and verifying that the floor of the excavation was reasonably level and smooth. The precision required for earth-sheltered construction exceeded that of conventional basements. Any irregularities in the floor would complicate the concrete work later, and any deviation from specified depths would affect the final relationship between the roof surface and surrounding grade. Jim Henderson drove past on County Road 43 3 times during the afternoon, slowing each time to observe the excavation. On his third pass, he pulled into Marcus's driveway and walked over to where Marcus stood watching Mike Johnson work the excavator controls. "You're really doing this," Jim said. It was not a question. "We're really doing this," Marcus confirmed. Jim shook his head slowly. "Marcus, I'm going to be honest with you. I think you're making a mistake. That thing is going to look like a bomb shelter, and it's going to hurt property values for all of us. My place is directly across from yours. When I try to sell someday, potential buyers are going to see your grass-covered mound and think they're moving next to a survivalist compound." Marcus had heard versions of this argument before, but Jim's directness was new. "Jim, we're 9/10 of a mile from your house. Trees block the view. No one looking at your property will even see my cabin unless they walk back into the woods specifically looking for it. People talk," Jim said. "Word gets around about weird stuff. Your underground house is going to be the thing people mention when they describe this area." Tommy had been listening to the conversation, and Marcus saw his son's face fall. The boy had been excited about the cabin project, but hearing a neighbor call it weird hurt. Marcus felt a flash of anger, but suppressed it. Arguing with Jim would accomplish nothing. "I appreciate your concern," Marcus said carefully. "But we're building this cabin whether you approve or not. The permit is issued. The excavation is happening. I'd prefer to have neighborly relations while we do it, but I understand if you need time to adjust to the idea." Jim looked at the excavation pit, at the stockpiled topsoil, at the forest surrounding the clearing. "Just try to make it not look too crazy, okay? Maybe plant some trees around it or something." "The entire roof will be covered in native prairie grasses," Marcus said. "It'll blend into the landscape better than a conventional structure. That's actually one of the advantages of earth-sheltered design: low visual impact." Jim walked back to his truck without responding. Marcus watched him drive away and then turned to find Tommy standing nearby, looking uncertain. "Dad, are we doing something wrong?" Marcus knelt down to his son's eye level. "No, Tommy, we're doing something different. Different makes some people uncomfortable because they don't understand it, but different isn't wrong. Remember that." The excavation was completed by 4:30 in the afternoon. Mike Johnson climbed down from the excavator and walked the perimeter of the pit with Marcus, checking measurements one final time. The hole measured exactly to specification, with clean vertical walls on 3 sides and a stepped grade on the 4th. Approximately 120 cubic yards of subsoil had been excavated and piled on the western side of the clearing. That soil would be used later to berm the northern and side walls of the structure, creating the earth-sheltered envelope that made the design work. "Never dug one like this before," Mike said, wiping sweat from his forehead. "Got to admit, I'm curious to see how it turns out." Marcus paid Mike his fee and watched the excavator drive away on the trailer behind Mike's truck. Then he stood at the edge of the excavation pit as the afternoon sun angled through the trees, casting long shadows across the exposed earth. This hole represented commitment. There was no backing out now, no changing his mind and building something conventional. His neighbors thought he was crazy. His wife was fighting cancer. His son was watching to see if his father's unusual ideas would prove brilliant or foolish. Marcus pulled out his phone and took a photograph of the empty excavation. Years from now, he wanted to remember this moment when the project existed only as potential, before concrete and waterproofing and soil transformed a hole in the ground into a home that would prove everyone wrong. Traditional residential construction began with a foundation, typically concrete footings poured below the frost line with concrete or block walls rising to support the structure above. Marcus's design eliminated the conventional foundation entirely, replacing it with a system that his building inspector had reluctantly approved after extensive documentation. Instead of footings and foundation walls, Marcus would pour reinforced concrete walls directly on a prepared gravel base, with the walls themselves serving as both foundation and structural envelope. The concept was simpler than conventional foundation systems, but required careful attention to detail. On July 30th, 2018, Marcus hired a small crew to prepare the excavation floor and install the gravel drainage system. The crew consisted of 2 brothers from Pine River, who normally worked on commercial construction, but were available for a week-long residential job. They arrived with a dump truck, carrying 12 cubic yards of crushed rock, and began spreading it across the floor of the excavation. The gravel layer served multiple purposes in Marcus's design. First, it provided a level base for the concrete walls, eliminating any irregularities in the excavated soil. Second, it created a drainage layer beneath the structure. Even with extensive exterior waterproofing, some moisture might eventually reach the base of the walls through capillary action or vapor diffusion. The gravel layer would collect that moisture and channel it to perimeter drains that would carry it away from the structure. Third, the crushed rock prevented frost heaving by interrupting the capillary rise of water from the subsoil, a critical consideration in Minnesota's freeze-thaw climate. Marcus had specified 3/4-inch crushed limestone rather than rounded river rock. The angular edges of crushed stone locked together when compacted, creating a stable base that would not shift under load. River rock, despite being cheaper, would have allowed movement over time as individual stones rolled and settled. The crew spread the gravel to a uniform depth of 8 inches and then compacted it using a plate compactor, making multiple passes until the surface was dense and level. Next came the perimeter drain installation. Marcus had designed a system using 4-inch perforated PVC pipe wrapped in filter fabric and surrounded by additional gravel. The drain pipe ran along the exterior base of where the concrete walls would be poured, with a slight slope toward the southeast corner, where the collected water would discharge to daylight down the property's natural grade. The system was overkill by conventional basement standards, but Marcus was not willing to risk moisture problems. A conventional basement might tolerate minor dampness. An earth-sheltered structure where people would live year-round could not. Tommy helped with the drainage installation, carefully wrapping filter fabric around the perforated pipe under Marcus's supervision. The boy took the responsibility seriously, understanding that his father trusted him with an important task. Sarah came out from their suburban home around noon with sandwiches and lemonade, and the crew took a break in the shade of the surrounding oaks. She looked thin and tired from chemotherapy, but she walked the perimeter of the excavation with genuine interest, asking questions about each component of the system. "How do you know this will work?" she asked Marcus quietly, away from the crew. "Because the physics are sound," Marcus said. "Water flows downhill. Gravel drains faster than soil. Concrete is impermeable when properly mixed and cured. We're not inventing new principles, just applying them carefully." "But if you're wrong," Sarah said, not finishing the sentence. "If I'm wrong, we have a wet basement and we fix it," Marcus said. "But I'm not wrong. I've checked these calculations dozens of times. I've consulted with engineers who have built similar structures. The risk isn't in the design, Sarah. The risk is in the execution. That's why I'm here every day, watching every step." The concrete pour was scheduled for August 2nd. Marcus had contracted with a local ready-mix company to deliver 36 cubic yards of concrete, enough to pour all 4 walls to their full height of 8 feet in a single continuous operation. Pouring the walls in one session eliminated cold joints where separate pours met, creating a monolithic structure with no weak points for water infiltration. The walls would be 12 inches thick, significantly thicker than the 8-inch block walls typical of conventional basements. The extra thickness provided additional thermal mass and structural strength to resist lateral earth pressure when the walls were backfilled. Marcus had designed a reinforcing steel pattern using No. 5 rebar at 12-inch spacing, both vertically and horizontally, creating a grid within the concrete that would prevent cracking under load. The day before the pour, Marcus and his crew built the formwork. Concrete forms for earth-sheltered construction were more complex than conventional foundation forms because they had to be braced against significant outward pressure as liquid concrete filled the space between inner and outer form panels. Marcus used 3/4-inch plywood for the form surfaces, backed by 2x4 studs at 16-inch centers, further braced by adjustable steel form ties that held the inner and outer panels exactly 12 inches apart. Building the forms took 2 full days. Marcus worked alongside his crew, checking every measurement, ensuring every brace was secure, verifying that the forms were perfectly plumb and level. Tommy watched from a safe distance, occasionally bringing tools or helping to clean up scrap lumber. The boy understood that this phase was critical, and that his father's focus could not be broken by questions or distractions. On the morning of August 2nd, the concrete trucks arrived at 7 o'clock. Marcus had ordered a special mix design with a lower water-cement ratio than standard concrete, making it denser and less permeable. The mix included a waterproofing admixture that would cause any cracks that developed to self-heal through crystalline growth when exposed to moisture. The concrete would cost approximately 20% more than standard mix, but the investment was worthwhile for a structure that would be permanently in contact with earth. The pour took 4 hours. 3 separate concrete trucks delivered their loads in sequence, with Marcus and his crew working continuously to place the concrete evenly around the formwork perimeter. They used vibrators to consolidate the concrete and eliminate air pockets, working carefully to avoid over-vibrating, which could cause segregation of the aggregate. As the concrete level rose within the forms, Marcus watched anxiously for any signs of formwork failure. The lateral pressure was enormous, and a blowout would be catastrophic, spilling tons of concrete and potentially injuring someone. The forms held perfectly. By 11 o'clock, all 4 walls were poured to their full 8-foot height, with the top surface struck level using a straight edge. The concrete would need to cure for at least 7 days before the forms could be stripped, and during that time it would need to be kept moist to prevent cracking. Marcus rigged a soaker hose system that would run periodically to maintain moisture on the exposed top surface. Dale Sorensen arrived for his foundation inspection on August 3rd, while the concrete was still curing within the forms. He could not see the walls themselves, but he inspected the drainage system, the gravel base, and the formwork construction. He spent 20 minutes reviewing Marcus's documentation and comparing it to the approved plans before finally signing off on the inspection card. "You better hope this works," Dale said before leaving, "because if these walls fail, you've got 36 yards of concrete that isn't going anywhere." Marcus did not respond. He knew the walls would not fail. The engineering was sound, the materials were appropriate, and the execution had been careful. What Dale saw as risk, Marcus understood as physics. Concrete did not care about skepticism. It simply performed according to its material properties, and those properties were well within the design parameters. On August 10th, Marcus stripped the forms. The concrete walls stood perfect and true, with smooth surfaces and sharp corners, exactly as designed. The structure that had existed only as calculations and drawings was now physical reality. A concrete envelope ready to be transformed into a home that would prove earth-sheltered architecture could work in modern residential construction. The roof represented the most unconventional element of Marcus's design, and the component that generated the most skepticism from contractors. Conventional roofs were designed to shed water as quickly as possible, using impermeable materials like asphalt shingles or metal panels installed on a sloped surface. Marcus's roof would do the opposite, holding thousands of pounds of saturated soil on a relatively flat surface, and relying on multiple integrated systems to manage water that would be absorbed into the growing medium rather than immediately shed. Construction of the living roof began on August 27, 2018, after the concrete walls had fully cured and been waterproofed. The first step was installing the roof structure itself, a system of engineered lumber beams spanning the 42-foot length of the building. Marcus had specified laminated veneer lumber beams rather than solid timber because LVL provided consistent strength properties without the natural defects of sawn lumber. Each beam was 16 inches deep and 3.5 inches wide, spaced 24 inches on center, creating a roof frame capable of supporting the extraordinary loads his design required. The beams rested on the concrete walls using metal beam hangers that transferred the roof load directly to the wall structure. Marcus had calculated the load distribution carefully. The soil layer would weigh approximately 90 pounds per square foot when saturated with water. The growing medium, drainage layers, waterproofing, and structural components added another 40 pounds per square foot. Snow load in their climate zone could reach 60 pounds per square foot during extreme winters. The total potential load approached 190 pounds per square foot, more than 3 times the load on a conventional roof. Setting the beams required a small crane, which Mike Johnson provided along with 2 workers to guide the beams into position. Each beam weighed approximately 400 pounds and had to be placed precisely so the hangers engaged correctly. Tommy watched from inside the concrete enclosure, fascinated by how the crane operator could control such massive pieces of lumber with apparent ease. The beam installation took 1 full day, with final adjustments made using pry bars and persuasive strikes from a sledgehammer. Once the beams were set, Marcus installed the roof decking. He used 3/4-inch tongue-and-groove plywood rated for exterior use, attached to the beams with construction adhesive and screws at 6-inch intervals. The decking had to be absolutely rigid because any flexing would compromise the waterproofing layers that would be installed on top. Marcus walked across each sheet after installation, feeling for any movement or soft spots. He found none. The roof deck was solid enough to support concentrated loads without deflection. The waterproofing system began with a layer of self-adhering rubberized asphalt membrane. This material, typically used for commercial flat roof applications, provided the primary water barrier. Marcus rolled out the membrane in overlapping sheets, carefully pressing it to the plywood deck to eliminate air bubbles and ensure complete adhesion. Each seam overlapped by 6 inches, and Marcus used a roller to compress the seams and activate the adhesive. The work was tedious and had to be done in moderate temperatures. Too hot, and the membrane became too sticky to work with. Too cold, and it would not adhere properly. Over the primary membrane, Marcus installed a second waterproofing layer using a different material, a high-density polyethylene sheet 40 mils thick. This layer served as redundant protection and as a root barrier. Plant roots seeking water and nutrients would eventually penetrate most materials given enough time, but HDPE was one of the few materials that remained root-resistant indefinitely. The polyethylene sheets were heat welded at the seams using a specialized tool that created molecular bonds stronger than the surrounding material. Tommy asked why 2 waterproofing layers were necessary if each was supposed to be waterproof on its own. Marcus explained the concept of redundancy. In engineering, we never rely on a single system for critical functions. If the polyethylene develops a pinhole from a rock in the soil, the membrane below it still provides protection. If the membrane fails at a seam, the polyethylene above it still keeps water out. The chance of both systems failing at the same location is essentially 0. Above the waterproofing came the drainage layer, a product called a drainage mat. This material consisted of a dimpled plastic sheet that created a 3-dimensional void space for water to move laterally across the roof surface. Without this drainage layer, water absorbed into the soil would have no way to escape except by slowly evaporating or percolating downward through the waterproofing, which would eventually cause problems. The drainage mat collected water and channeled it to perimeter drains at the roof edges. The drainage mat was light and easy to install, but it had to be positioned carefully to ensure the dimples faced upward, creating the void space for water flow. Marcus rolled out the material across the entire roof surface, cutting it to fit around the chimney penetrations that would eventually vent the heating system and provide fresh air intake. The mat overlapped its seams by 12 inches, and Marcus secured it with plastic stakes driven through into the decking below. Over the drainage mat came a layer of filter fabric, a geotextile material that prevented soil particles from washing down into the drainage layer and clogging the void spaces. The fabric was permeable to water, but impermeable to soil, functioning like a coffee filter on a massive scale. Marcus had purchased enough fabric to cover the entire roof with a single continuous sheet, eliminating seams that might allow soil to pass through. The fabric was lightweight and awkward to handle in even light wind, so Marcus waited for a calm morning to install it, using Tommy and Sarah to hold edges while he positioned and secured it. Finally came the soil itself. Marcus had calculated that 24 inches of soil depth would provide adequate insulation value and sufficient rooting depth for native prairie grasses while remaining within his structural load capacity. The soil composition was critical. Standard topsoil would be too heavy when saturated and would compact over time, reducing drainage and plant health. Marcus had researched growing medium specifications for green roofs and developed a custom blend: 60% sand, 25% compost, 10% expanded clay aggregate, and 5% topsoil for microbial content. The expanded clay aggregate was the key ingredient. These lightweight porous granules absorbed water like a sponge, but weighed far less than soil. They improved drainage while maintaining moisture availability for plant roots, and they would not decompose or compact over time. The material was expensive, nearly $8 per cubic foot, but Marcus needed only 3 cubic yards mixed into his total growing medium volume of 30 cubic yards. Transporting 30 cubic yards of custom soil blend onto a roof 8 feet above grade presented a logistical challenge. Marcus rented a small conveyor belt system designed for concrete work and positioned it to carry soil from a staging pile at ground level up to the roof surface. Tommy operated the controls under his father's supervision, while Marcus and his crew spread the soil evenly across the roof, working outward from the conveyor discharge point. The soil installation took 3 days. Marcus used a laser level to ensure even depth across the entire roof surface, checking and rechecking measurements as the work progressed. At the perimeter edges, he installed a wooden curb to contain the soil and prevent erosion. The curb was constructed from cedar lumber naturally resistant to decay, set back slightly from the roof edge to create a drainage channel. By September 20th, the living roof was structurally complete but visually raw, a rectangle of brown soil sitting atop concrete walls, looking more like an abandoned construction project than a revolutionary building. The transformation would come later when native grasses established themselves and turned the roof into a living ecosystem. But even in its unfinished state, the roof represented validation of Marcus's engineering. The structure supported the massive load without visible deflection. The waterproofing remained intact. The drainage system functioned as designed, channeling water away from the building during a rain shower that occurred 2 days after soil installation. Jim Henderson drove past several times during roof construction and eventually stopped to ask a question that had apparently been bothering him. What happens when that soil freezes? Won't it expand and push your walls apart? Marcus had anticipated this question because it represented a common misconception about earth-sheltered design. Soil freezes from the surface downward, he explained. The frost depth here is around 42 inches, which means in the coldest winters, the top 3.5 feet of soil on the roof might freeze. But frozen soil doesn't expand laterally with significant force. It's not like water in a closed container. The soil is loose and can accommodate the volumetric expansion of ice formation without generating lateral pressure. Jim did not look convinced, but he did not argue. He simply shook his head and drove away, leaving Marcus to continue spreading soil on a roof that would ultimately prove more durable and better insulated than the asphalt shingles covering Jim Henderson's conventional home. The Firewood storage system represented one of Marcus's most practical innovations, born from observing how his neighbors struggled with moisture management. Traditional wood piles stood exposed to weather, covered at best with tarps that inevitably leaked or blew away. Marcus integrated firewood storage directly into the building envelope, creating alcoves that protected wood while leveraging thermal mass for passive drying. The alcoves were built into the southern exposure, where 3 separate recesses, each 7 feet wide and 4 feet deep, were framed into the concrete wall structure before backfilling. Marcus used pressure-treated lumber to create internal framing within these spaces, installing slatted floors elevated 6 inches above the concrete base to promote air circulation. The alcove ceilings consisted of the main roof structure, but the massive overhang extended 5 feet beyond the wall face, creating horizontal protection even during severe weather with wind-driven precipitation. Each alcove could hold approximately 1 cord of split firewood stacked to a height of 6 feet. The 3-cord total capacity would supply their heating needs for an entire winter with a comfortable margin. But the alcoves provided more than simple storage. The concrete walls retained heat from the interior living space, and that thermal energy radiated into the alcoves, creating a passive drying effect that actually improved wood quality over time. Freshly split wood at 25% moisture content would gradually dry to 15%, the optimal level for efficient burning, simply from exposure to the alcove environment. Marcus designed a dual chimney system that served multiple functions while becoming the most visible exterior feature of the earth-sheltered structure. The chimneys would rise 4 feet above the soil-covered roof, making them the only elements clearly visible from a distance. Rather than using metal flue pipes, Marcus chose to build traditional masonry chimneys using local fieldstone, both for aesthetic reasons and for thermal performance. The western chimney served the primary heating system, a high-efficiency wood stove that Marcus had selected for its clean burn technology and heat output characteristics. The eastern chimney housed the fresh air intake for the mechanical ventilation system and provided a secondary heating option. Marcus had researched rocket mass heaters extensively and incorporated elements of that design into his secondary heating system, creating a masonry heater that would absorb heat from combustion and release it slowly over many hours. Building the chimneys required masonry skills Marcus did not possess, so he hired a stonemason named Carl Peterson, who had 40 years of experience and a reputation for quality work. Carl arrived in early October of 2018 and spent 3 weeks constructing the chimneys stone by stone. He selected each piece of fieldstone for size, shape, and thermal properties, fitting them together with minimal mortar. Marcus designed the interior climate control system around the principle that the best energy is energy you never need to use. The earth-sheltered envelope provided baseline temperature stability, maintaining interior temperatures between 55 and 60 degrees Fahrenheit year-round, with no mechanical input. This natural thermal mass effect eliminated the extreme temperature swings that plagued conventional structures and reduced heating and cooling loads by approximately 75% compared to above-ground construction. The mechanical ventilation system consisted of an energy recovery ventilator that exchanged stale interior air with fresh outside air while transferring heat between the airstreams. During winter, the ERV captured heat from exhaust air and transferred it to incoming fresh air, recovering up to 80% of the thermal energy that would otherwise be lost. During summer, the process reversed, pre-cooling incoming air using the cooler exhaust air. The system provided continuous fresh air circulation without the energy penalty of simply opening windows. Humidity management was controlled through a combination of the ERV system and the hygroscopic properties of the interior materials. Marcus had finished interior walls with lime plaster rather than drywall. Lime plaster could absorb and release moisture vapor, naturally moderating indoor humidity levels between 40 and 60%, without mechanical dehumidification. October 27, 2018 arrived with temperatures in the low 40s and overcast skies threatening early snow. Marcus and Sarah moved their essential belongings from their suburban rental into the completed cabin, transforming an engineering project into a home. Tommy carried his own boxes, carefully placing his books and toys in the bedroom Marcus had built for him on the eastern side of the structure. The interior was sparse but functional. Marcus had built simple furniture from lumber salvaged during construction: a bed frame, a table, shelving units. The lime plaster walls were still curing, their white surface gradually carbonating as they absorbed carbon dioxide from the air. The polished concrete floors reflected light from the south-facing windows, making the space feel larger than its 1,000 square feet. Sarah walked through each room slowly, running her hand along the stone chimney, testing the water at the kitchen sink, adjusting the thermostat on the wood stove that would provide their primary heat. She had lived with Marcus's obsession for 18 months, watching drawings transform into reality while fighting her own battle with cancer. Now she stood in a home built from determination and calculation, a structure that existed because her husband refused to accept conventional limitations. "It feels solid," she said finally, "like nothing could touch us here." January of 2019 brought the polar vortex, a meteorological event that pushed Arctic air masses deep into the continental United States. Temperatures across Minnesota dropped to -30 degrees Fahrenheit, with wind chills reaching -50. The extreme cold lasted 5 days, testing every heating system in the region and exposing the weaknesses of conventional construction. Jim Henderson's natural gas bill for January exceeded $400, triple his normal winter cost. Karen Mills, 2 properties down, ran space heaters continuously, overloading a circuit and requiring an emergency electrician visit. Other neighbors burned through firewood supplies at alarming rates, worried they would run short before spring. Inside the earth-sheltered cabin, Marcus monitored temperatures with scientific precision. The exterior temperature reached -28 on January 30th. The interior temperature, with the wood stove burning at moderate output, remained at 68 degrees. Marcus calculated that they consumed approximately 1/8 cord of firewood during the 5-day cold snap, roughly $40 worth of wood to maintain comfort, while his neighbors spent hundreds on conventional heating. Tommy invited a school friend to visit during the polar vortex. The boy, accustomed to the drafty cold near windows in conventional homes, kept asking why he could not feel cold air anywhere in the cabin. Marcus explained thermal mass and continuous insulation, concepts the child could not fully grasp, but intuitively understood meant something was different about how this house worked. July of 2019 brought an extended heat wave with temperatures exceeding 95 degrees Fahrenheit for 12 consecutive days. Humidity levels climbed above 70%, creating heat index values approaching 110 degrees. The combination stressed air conditioning systems throughout the region, causing multiple compressor failures and driving electricity demand to record levels. Marcus's neighbors ran their air conditioners continuously. Jim Henderson's electric bill reached $340 for the month. Several families retreated to their basements during the hottest afternoon hours, seeking relief in the coolest parts of their homes. The local hardware store sold out of window fans and portable air conditioners. The earth-sheltered cabin maintained an interior temperature of 68 degrees without any cooling input. Marcus opened windows in the evening to flush warm air accumulated during the day, and he closed them in the morning to trap the cool night air inside. The thermal mass of the surrounding earth absorbed excess heat slowly, preventing interior temperature rise even when exterior temperatures remained extreme for days. Sarah, now in remission and regaining strength, invited neighbors for coffee during the heat wave. Karen Mills arrived expecting to find the cabin uncomfortably warm and was stunned to discover she needed a sweater. "How is this possible?" she asked, touching the cool lime plaster walls. Marcus explained the principle simply. Earth temperature at 6 feet depth stays around 55 degrees year-round. Our walls are in contact with that stable temperature. The building can't get hot because it's surrounded by a massive heat sink. The freezing rain that began on November 7, 2019, returned Marcus to the present moment. He had spent 18 months building, testing, and proving his design. Now nature was providing the most dramatic validation yet. From his position at the cabin door, Marcus watched Jim Henderson finally give up trying to cover his firewood and retreat inside his house, defeated by weather he should have prepared for. The storm continued for 3 full days. Ice accumulated on every surface, bringing down power lines and tree branches throughout the township. Marcus's cabin lost electricity on the second day, but the outage was irrelevant. Their lighting ran on 12-volt LED fixtures, powered by a small battery bank charged by solar panels Marcus had installed on the south-facing roof section that remained clear of soil. Their heat came from wood that stayed dry regardless of weather. Their water came from a well with a hand pump backup. Tommy spent the storm days reading by the wood stove, occasionally going outside with Bear to explore the ice-transformed landscape. The dog seemed to enjoy the freezing rain, his thick coat shedding water and ice crystals as he bounded through the drifts. Sarah made soup on the wood stove, the cast-iron pot simmering for hours and filling the cabin with the smell of vegetables and herbs from their small summer garden. On the third day, Jim Henderson knocked on their door, looking exhausted and embarrassed. Jim Henderson stood in Marcus's doorway holding a thermos of coffee, an offering, and an admission. "My firewood's ruined," he said without preamble. 3 cords soaked through. It won't burn worth a damn. I'm running my furnace full-time and the gas company is going to kill me on this month's bill. Marcus invited him inside. Jim looked around the cabin interior with new eyes, no longer seeing an eccentric project but a functional solution to problems he was currently experiencing. He noticed the dry firewood stacked neatly in the alcoves visible through the southern windows. He felt the comfortable temperature maintained without obvious heating system noise. He saw Sarah and Tommy going about their daily activities as if a historic ice storm were not occurring outside. "I was wrong," Jim said finally. "I should have said that 18 months ago, but I'm saying it now. This design works. You knew what you were doing, and I dismissed it because it looked different." Marcus accepted the apology with a nod. "The physics didn't care whether you approved, but I appreciate you saying it." Jim asked detailed questions about construction costs, heating expenses, and whether the design could be modified for a conventional above-ground structure. Marcus answered honestly. The techniques could be adapted, but the full benefits required earth contact. A well-insulated conventional house would outperform Jim's current home, but could not match the thermal stability of earth sheltering. Word spread through the township. By December, Marcus had received visits from 4 other neighbors asking about his design. Spring of 2020 arrived with Tommy, now 11 years old, selecting the earth-sheltered cabin as his science fair project topic. He titled his presentation, "Thermal Mass and Energy Efficiency in Earth-Sheltered Architecture," and spent weeks documenting temperature data, energy consumption, and cost comparisons between his family's cabin and conventional homes. His teacher initially questioned whether the project was too advanced for 5th grade, but Tommy's genuine understanding of the concepts convinced her otherwise. Tommy's presentation board included photographs of the construction process, graphs showing interior temperature stability across seasons, and calculations demonstrating energy savings. He brought classmates home to tour the cabin, explaining how earth temperature remained constant, how the living roof provided insulation, and how the firewood alcoves prevented moisture damage. The children were fascinated by the idea that a house could work with nature rather than fighting against it. He won first place at the school science fair and advanced to regional competition, where he placed 3rd among middle school entries despite being 2 years younger than most competitors. More importantly, his project sparked conversations among parents about alternative building methods and energy efficiency. Bear, now 3 years old, had become the cabin's unofficial guardian, sleeping near the wood stove and alerting the family to visitors or wildlife approaching through the surrounding forest. January of 2024 found Marcus standing in his firewood alcove during another Minnesota winter, this one milder than the polar vortex 5 years earlier, but still cold enough to test heating systems. 7 earth-sheltered homes now existed within a 20-mile radius of his cabin, each built by families who had visited his structure and recognized the practical advantages. Marcus had consulted on 4 of those projects, sharing his techniques freely and helping others avoid the mistakes he had made during his learning process. His consulting work had become a modest side business, generating $15,000 annually, money that helped pay down the medical debt that still lingered from Sarah's treatment. Sarah herself had been in remission for 4 years, her prognosis increasingly positive with each clean scan. She had returned to part-time work as a teacher and spent weekends tending the native prairie grasses on their living roof, which had matured into a diverse ecosystem supporting butterflies, birds, and beneficial insects. Tommy, now 15, talked about studying environmental engineering in college. He had grown up in a home that demonstrated sustainable design principles and had developed an intuitive understanding that most adults lacked. His friends considered the cabin normal, a reminder that what seemed radical to one generation could become ordinary to the next. The cabin itself had required minimal maintenance over 5 years. The living roof grasses grew and died back seasonally. The wood stove needed annual cleaning. The mechanical systems required filter changes. But the fundamental structure remained exactly as Marcus had built it, requiring no repairs and showing no signs of the deterioration that plagued conventional construction. The concrete walls, the waterproofing layers, the thermal mass that moderated temperature, all of it functioned precisely as the engineering had predicted. Jim Henderson had become an advocate for earth-sheltered design after living through 3 more severe weather events that left his conventional home struggling while Marcus's cabin remained comfortable. He had even apologized publicly at a township meeting, admitting his initial mockery had been based on ignorance rather than understanding. Other neighbors who had questioned the design now pointed to it as an example of innovative thinking solving real problems. Marcus sometimes stood at his cabin door, as he had during the freezing rainstorm of 2019, watching weather events that would have been catastrophic for his family if they had built conventionally. The firewood stayed dry in its alcoves. The interior temperature remained stable. The structure that neighbors had called a bunker had become a home that proved sustainable design was not about sacrifice or discomfort, but about understanding how buildings could work with natural systems rather than against them. The impossible had become routine, carved not into history books, but built into earth and concrete and the accumulated experience of families who chose to build differently. Marcus Chen's obsession with survival had created something more valuable than shelter. It had created a demonstration that alternative thinking could solve problems conventional wisdom could not address, and that sometimes the craziest ideas were simply ideas whose time had finally come.